Welcome to this explainer, where we're jumping straight into one of chemistry's absolute most mind-bending phenomena. We all know that microscopic building blocks construct our reality, right? But what happens when the exact same set of atoms just decides to build completely different worlds?
Think about trying to catch a molecular identity thief. They share the exact same chemical fingerprint down to the very last atom, but they wear a completely different disguise. If you count the carbon, hydrogen, and oxygen atoms, they match perfectly. But when you actually look at how they act, how they smell, or how they react to their environment, they're total strangers. So, this brings us to the realm of isomerism. It's that core rule of organic chemistry that reminds us that a molecular formula, well, that's really only half the story. It's not just about the ingredients you have, it's the physical architecture that dictates a substance's true identity. Today, we're navigating through the classification tree of isomerism, mapping out exactly how these molecular doppelgangers operate. We're going to start with static disguises, where the structure is permanently fixed, and work our way all the way down to dynamic, real-time shapeshifters. So let's start right at the foundation.
First up, we're looking at the static disguises, otherwise known as structural isomerism.
Kicking things off with chain isomerism, this is where the fundamental atomic skeleton of the molecule is permanently rewired. Take N-butane and isobutane. They share the exact same carbon count, 4 carbons, 10 hydrogens, but the structural divergence is wild. One forms this long, straight line, while the other branches out like a tree. And just because of that branching, their packing efficiency changes entirely, giving them completely different boiling and melting points. Then we have positional isomerism. Here, the carbon skeleton stays exactly the same, but the key functional group, or a double bond, simply moves to a different address along the chain. It's kind of like taking the front door of a house and moving it to the side. It's the exact same house, but the way you interact with it changes entirely. So, what happens when the disguise goes a bit deeper and the molecule completely changes its chemical identity? Let's get into functional isomers and metamers. This brings us to functional isomerism, where the very same formula yields completely different classes of compounds. Take C2H6O, for example. Arranged one way, it's ethanol, a liquid alcohol. But rearrange those exact same atoms, and you get methoxymethane, an ether that is literally a gas at room temperature. Think about that for a second. You transform a liquid into a gas just by shuffling a single oxygen atom. And then there's metamerism. This is an incredibly sneaky disguise. Here, the functional group stays the same, but the carbons are distributed unevenly. In ethers, for instance, the oxygen acts as the bridge. Sometimes it's perfectly balanced with 2 carbons on each side, but if you shift that to 1 on the left and 3 on the right, that slight imbalance yields a totally distinct metamer. All right, now we arrive at the ultimate shapeshifters, Tautomerism. These are the molecules that absolutely refuse to pick just one disguise. Okay, so the absolutely crucial point here is to separate Tautomerism from resonance. Resonance is really a hypothetical concept we use to model molecules, right? The atoms themselves are fixed in place. But Tautomerism, that is completely real. It involves the actual physical shift of a hydrogen atom and a double bond, simultaneously jumping across the molecule in real time. And this forms completely isolatable structures with totally different functional groups.
The heavyweight champion of these dynamic shifts is definitely keto-enol tautomerism, which operates on a triad system. What happens is a hydrogen atom constantly oscillates back and forth between a carbon and an oxygen atom. When the hydrogen is hanging out on the carbon, you've got the keto form. But when it jumps over to the oxygen, a double bond shifts, and boom, you suddenly have an enol form. They exist in this dynamic equilibrium, just constantly morphing back and forth. Now, these molecular morphs don't just happen at random. They are governed by some very strict rules of engagement, including essential conditions and stability factors. The golden rule for keto-enol tautomerism is the presence of an alpha hydrogen atom. That's a hydrogen attached to the carbon sitting right next door to the carbon-oxygen double bond. Without that specific hydrogen to make the jump, the molecule is completely locked out of the shape-shifting game entirely. This is exactly why molecules like benzaldehyde, which lack that crucial alpha hydrogen, just can't participate at all. They are permanently frozen in their keto form. Usually, the keto form is the undisputed champion of stability, completely dominating the mixture. But there are some brilliant exceptions. Take acetyl acetone. In this specific system, the enol form actually takes over, representing a massive 76% of the mixture. And why is that? Well, because when it morphs into the enol form, it creates an incredibly stable six-membered ring locked in place by internal hydrogen bonding. The molecule effectively grabs onto itself, creating a highly stable conjugated structure that totally beats the standard keto form.
What's even wilder is that the surrounding environment actually acts as a director in this whole play. If you dissolve that exact same molecule in a nonpolar solvent like hexane, the enol form absolutely thrives, hitting 92%. But the moment you drop it into a highly polar environment like water, those water molecules rush in and completely disrupt those beautiful internal hydrogen bonds. Suddenly, the enol form crashes down to just 15%. The molecule literally changes its shape simply based on what it's swimming in.
And what makes this dynamic equilibrium so incredibly versatile is that these rapid atomic shifts can be actively triggered. It's not just a passive process. The shape-shifting can be catalyzed by both acidic and basic environments. The presence of extra protons in an acid or hydroxide ions in a base acts almost like a molecular cattle prod. It speeds up the transfer of that jumping hydrogen atom, getting the molecule to rapidly switch its identity. Ultimately, these fundamental micro-rules scale way up. They govern massive, complex molecular structures, like cyclic and phenyl compounds. In these larger systems, it becomes this fascinating tug-of-war. The push and pull of aromaticity, structural strain, and extended conjugation actually decide which identity the molecule is going to assume. If a molecule can morph into a state that gives it aromatic stability, that highly stable ring of electrons, it will absolutely take that path, favoring the enol form just to reach that much lower energy state.
So, by looking closely at isomerism, we've gone from fixed structural branches all the way to molecules that actively swap their functional groups based on their environment. And it leaves us with a truly profound realization. The physical world we rely on, the materials we literally touch and use every single day, are built by shapeshifters constantly trading identities in the blink of an eye. So I want to leave you with this. If the microscopic building blocks of our universe are truly this fluid, how fixed is the reality we actually see around us?